Ice, ice, baby!
In our last video, we set the goal to find a mathematical description of the impedance of an electrochemical reaction under the conditions of linear semi-infinite diffusion. As there's no electrical circuit element which shows a comparable impedance response, Sebastian derived an expression based on physico-chemical concept and respective equations. For this, we analyzed the problem to identify essential processes that we must consider for a sufficient description. We have an electrode-electrolyte interface at position x equals 0 and consider only the direction perpendicular to the electrode into the electrolyte. Electron transfer takes place at the interface and the associated kinetic hindrance can be described by the Butler-Volmer theory. When concentration changes are induced at the electrode surface by a potential perturbation, species are transported down time-dependent concentration gradients, which is expressed by fixed diffusion laws. In impedance spectroscopy, the alternating potential at the electrode changes the concentration of oxidized and reduced species at the electrode periodically. This induces a periodic change to the concentration gradient in front of the electrode, which then propagates into the electrolyte. Because we ensure a linear, time-invariant system through the conditions we choose, such as low amplitude perturbation, only the perturbation frequency appears in the response throughout, be that in the current or in the concentrations. If we were dealing only with quantities at the interface, we could use our convenient description of a rotating phasor containing the familiar two pieces of information: amplitude and phase shift, as we do to describe the applied potential perturbation itself. For diffusion, however, concentrations away from the electrode determine the gradient and thereby the diffusive flux and the current we measure. If we want to continue using our description in the complex plane, there must be concentration phasors for all the points on X that matter, at the interface and in the electrolyte. Our complex phasors C tilde are therefore now functions of X, and their shape and extent governs what current response we measure. For the mathematical derivation, we need a general expression for the current density. The current density, as an electrochemical form of a reaction rate, depends on the concentrations immediately in front of the electrode. These in turn depend on the transport to and away from the electrode, so that we describe the change of the concentration gradient over time due to diffusion and plug in Fick's second law. Considering the respective boundary conditions for our case of semi-infinite diffusion, we arrive at a concentration profile decreasing exponentially in amplitude with increasing distance from the electrode. For higher frequencies, these deviations from the concentrations in the operating point decay over a shorter distance than at lower frequencies. Note that these profiles here are snapshots in time and in reality oscillate with the frequency of the applied potential perturbation as shown in our simulation. The heterogeneous rate constants then can be expressed using the Butler-Volmer theory, and we linearize the current response resulting from the potential and concentration perturbations according to the chosen conditions. Finally, we obtain the following equation for the interfacial Faradaic impedance in the presence of linear semi-infinite diffusion. In this video, we developed an improved intuition for this impedance and use it together with electrical circuit elements in an equivalent circuit to see the effect of different bulk concentrations of a redox couple on impedance spectra.
In our last video, we have derived an expression for the impedance under the condition of linear semi-infinite diffusion, and we have also considered electron transfer kinetic hindrance. And for this example, we had considered a reaction where an oxidized species takes up n electrons and reacts to a reduced species. Now keep in mind that to derive this impedance we had not yet considered influences, for example, of the electrolyte resistance or of the double layer capacitance. This will come at a later point in this video. Now if we look at this term, well, it looks quite complicated, but we can structure it a little bit. So in the first part we have a term that has the dimension of an area-specific resistance. So we divided the potential phasor with a current density phasor. So we would have to multiply that with the geometric electrode area to get a viable impedance in the dimension of ohms. But in any case, we have a real part of the equation and a part that contains information about the diffusion here, where we have a square root of j term in there. So the first part of this impedance, because it has the dimension of ohm, we can call that the charge transfer resistance. So let me mark this here in red. Call it R charge transfer. The second part of this equation, as I said, keeps maintains the influence here of the diffusion and the solution of these equations, and we already call this the Warburg impedance. Now, as you have noticed, this term still contains information about the kinetic hindrance. So there's the forward rate constant, for example, in here, the backward rate constant, and also this symmetry parameter, this alpha from the Butler-Fulmer kinetics. Now, we would like to simplify this equation, because in some cases we might be dealing with a reaction where we can neglect the electron transfer kinetic hindrance. And then we would like to describe this with a term that only contains information about the diffusion impedance. And for this purpose, let's think about what it means to consider the electron kinetic hindrance. If we ignore this, then the concentrations directly in front of the electrode at x equals 0 will be immediately determined by the potential at the electrode, and more specifically by the equilibrium constant that is potential dependent at the electrode. So we can essentially express the concentrations there as via the mass action law. So let's simplify this equation and write the mass action law for this. So no kinetic hindrance. So for the mass action law, let's write here, we have the potential dependent, in this case equilibrium constant, which is, well, the ratio between the concentration of the reduced species, the product, at x equals 0, and the reactant, the oxidized species at equals 0. But this equilibrium constant is also the quotient between the reaction rates of the forward reaction and the backward reaction. And this already is an expression that we can use to simplify our term up here. In our term here, we have so far written this with the reaction constants k forward, k backward, and the concentrations at the DC operating point. So let's keep this formalism and add these indices for the DC operating point also to this equation when we apply the mass action law at the DC operating point. And now, to substitute this expression in here, let us express the backward rate constant in this instance as a function of the forward rate constant. And this will, after rearranging the equation, result in k backward DC is equal to K forward dc and the quotient of the oxidized divided by the reduced species. At x equals 0. And now, armed with this simplification, we can go over to our Warburg impedance, or generalized Warburg impedance, and simplify it for the special case where we disregard or have no kinetic hindrance. So, we have Z Warburg simplified. And this will be equal to the following. So first of all, we keep this RT over NF squared term. Nothing happens to that. And now, let's plug in this equation here. We have here the backward rate constant and in this location, both in the numerator and denominator. And we will put in this expression here instead of that. So what we have is a very large fraction. We maintain so far K forward dc divided by square root of J omega dO. Keep in mind this is the diffusion coefficient, and all the signs that I'm using in these equations you can also read up on here. And now here we plug in this expression, and this means that we have now the forward rate constant, K forward dc, times this concentration relation here, CO dc divided by CR dc. And keep in mind, we had the square root term here, 1 over square root of J omega dr. And now in the denominator, we still have alpha times K forward dc times the concentration of the oxidized species, CO dc. However, now we substitute again the backward rate constant. So we have 1 minus alpha times K forward times the concentration relation. Times the concentration of the reduced species still from up here. And now let's simplify. First of all, what we notice is that these concentrations cancel out. They're gone. The second thing that we notice, due to our substitution, every single term in these two sums now contains the forward rate constant. So it's here, 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 and here. And that means that we can draw them out, and all of them cancel each other out, simplifying the equation quite considerably. And the last thing that we might want to have a look at is the denominator. So in the denominator, we now have a term remaining that reads alpha times CO dc plus 1 minus alpha times CO dc. So in essence, what we have is alpha plus 1 minus alpha, and in that case, well, what remains is 1. So only 1 times CO dc remains. Let's write the simplified term now in new line. Our prefactor remains here. And we get the expression 1 over square root J omega dO plus CO dc divided by CR dc times 1 over the square root of J omega dr. And the entire term is now divided only by CO dc. And this expression immediately simplifies further, because we can write this entire fraction on basically one set of numerators and denominators. So that means the CO appears here in this term of the sum, and in this term of the sum it cancels out immediately. So the final result of a simplification will be RT divided by NF squared times (1 over CO dc times the square root of j omega do plus the analog term, not forget the brackets here, 1 over CR dc times the square root of j omega dr. What we have now is a term that expresses the impedance that results from only the influence of linear semi-infinite diffusion when we neglect any kind of kinetic hindrance and simplify the term accordingly. And you can easily check this because no longer does any of the rate constants actually appear here. And now it's only a function of, for example, the concentration of the oxidized and reduced species and their diffusion coefficients. We now have a pretty simplified term for the Warburg impedance that characterizes linear semi-infinite diffusion. However, it would be quite nice to know what this looks like when we plot it in the Nyquist plot or when we obtain it in our experiment. And for this, we would like to know what the phase relations here are and what the dependence on the angular frequency is. And for this, we will have to do some more transformations to this term. First of all, you may notice that j and omega both appear in the square root here in these brackets. And so let's draw them out and deal with them further. The first term that we get is a term 1 over square root of j, the imaginary unit. And then the omega dependence, 1 over square root of omega. And then what remains of this prefactor here, RT over NF squared, times in brackets 1 over the concentration of the oxidized species times the square root of its diffusion coefficient and the analogous term for the reduced species. So clearly, we now have a dependence where it's dependent on the 1 over the square root of omega. So as the angular frequency gets lower, this impedance rises, but not linearly, but dependent on the square root of omega. However, the phase relations are not immediately obvious, because we have a term here, 1 over square root of j, where we don't immediately know what that even means. And to figure out what that means, let's have a brief recap of the notation of complex numbers and move on from there. Complex numbers are located in the complex plane. And in the complex plane, we have an imaginary axis and a real axis. And any complex number, for example, I will name it z, is located somewhere in this plane. Let's choose, for example, a number z that is located here. And the first way to write the coordinates of this complex number is to write the real part of z plus j times the imaginary part of z. The second way to interpret this complex number is by using Euler's notation. And for this, we basically interpret this complex number as something of a vector, which has a length and a phase angle under which it is rotated against the real axis. So this phase angle I will call phi z, and this length is called the magnitude of z. And if we note this here, then what we get is a notation where we have the length of this vector essentially times its rotation, where we have Euler's number to the power of j times the phase angle. And the last way to write the complex number is by using the trigonometric functions on this angle relation. So if we wanted to calculate from Euler's notation what the real and the imaginary part were, we would have to take the real part, where we have basically the projection onto the real axis, and we would have to take the cosine of phi z times the magnitude. So we maintain this term, and we have the real part, cosine of phi z. And then we have the imaginary part, where we have the sine of phi z. So we have plus j times sine of phi z. If we think about where the imaginary unit j actually is located in this plot, it is located on the imaginary axis, and it is in a distance of 1 from the origin. So this here is where the imaginary unit j is located. And with that knowledge, let's analyze what this term 1 over square root of j actually means. 1 over square root of j can be rewritten as j to the minus 1/2. And as we've now figured out, j itself can be written in Euler's notation as well, distance 1, so that doesn't appear, times e to the j pi half, because it's rotated 90 degrees. And this term is still taken to the power of minus 1/2. If we resolve this expression, we have to multiply the exponents, and we obtain e to the minus j pi fourth. And now, if we want to return to something that has a real and an imaginary part that we can immediately read off, let's return to this trigonometric notation here, where we have this. The length is still 1, and we take the cosine of phi z. So we take the cosine of minus pi fourth to get the real part, and the sine of minus pi fourth to get the imaginary part. And what we end up with is, well, these sines and cosines are both square root of 2 over 2, except that for the sine of this result is negative. So what we get is square root of 2 divided by 2 times the cosine of minus pi fourth, which is, well, remains 1 here, minus j. And now, if we finally simplify this to its fullest extent, we can divide square root of 2 times by 2, and we obtain 1 over square root of 2, because of course 2 is composed of square root 2 times square root 2. And now with that, we can figure out where this term is located in the complex plane. And it is at a location where the real and the negative imaginary part are equal. So this has a 45-degree negative angle here. And it is in a distance of 1 over square root of 2, which is something like 0.7. So let's put this here, minus 45 degrees. And this is 1 over square root of j. And now that we know this, we can go back to our Warburg impedance and clearly separate real and imaginary part. So we still have the relation with the omega, with the angular frequency. We get an additional term, 1 over square root of 2. And this stays exactly the same. And we add the term for the reduced species again. And now real and imaginary part are contained in this term 1 minus j. And what we notice in this term is that what is written in the middle here is just a factor. This is a number we can calculate once we know all the components, for example the diffusion coefficients or the concentrations, and we can term this number the Warburg coefficient sigma. And then what remains is a term that governs the frequency dependence, and we can write this entire term for the Warburg impedance quite simply as sigma over square root of omega times 1 minus j, which we may multiply out to get explicitly real and imaginary part, which are then sigma divided by square root of omega minus j times sigma divided by square root of omega. And now, let us think about how to plot this in a Nyquist plot. In the Nyquist plot, we usually plot the negative imaginary axis over the real axis. And from this term, what we see is that the real part is equal to the negative imaginary part. So whereas the negative 45-degree phase angle here is plotted in the fourth quadrant down here, because we take the negative imaginary axis, it's now plotted like this. And the frequency dependence is such that as the frequency gets lower, proportional to the square root, the impedance gets larger. So what we will measure at increasingly low frequencies is the line that starts somewhere in the origin and extends over here. We can connect the dots that we will measure and get a line under a 45-degree angle. This line is what we saw in Oliver's experiment. However, there was also a real axis offset. So clearly, there are more things that we need to consider if we want to describe a system fully. Considering different processes and their influence on the impedance spectrum is something that we had done extensively in our first introductory video series, Basics of EIS. And the approach we had chosen was to introduce equivalent circuits with different elements modeling different processes. However, our approach in this video series was different. We had physico-chemical systems described by equations, and we derived an expression for the impedance relating the potential phasor and the current density phasor in this case from the results from calculations from this equation. And the beauty of the impedance method is that these impedances are of equal rank. We can combine them to explain different phenomena, and so we can use an expression derived in this way in an equivalent circuit element. If we briefly recall what we had modeled with a Warburg impedance, linear semi-infinite diffusion, but we had also taken into account in our general derivation kinetic or electron transfer kinetic hindrances. And those together we modeled with a total impedance, in this case, with a Faradaic impedance, as we might call it, consisting of a charge transfer resistor and the Warburg impedance, modeling the influence of linear semi-infinite diffusion. And now, let's introduce these elements into an equivalent circuit, modeling further processes in the system. First of all, we must take account of the electrolyte resistance as we saw, a real axis offset, for example in Oliver's experiment. And this electrolyte resistance is a function of the conductivity of the electrolyte. We further have a double layer capacitor, C double layer, and now from our physico-chemical model we have an expression for what the impedance looks like for an applied potential perturbation when we take account of linear semi-infinite diffusion. And this is just the charge transfer resistance and the added Warburg impedance. Where we have R charge transfer and Z Warburg. And in this way, we have found an equivalent circuit that combines the influences of different phenomena. Now, let us have a look at what the impedance plot looks like in the Nyquist plot. For this, let's draw once more on negative imaginary axis. And our real axis. And let's begin to construct this spectrum. First of all, we have a real axis offset originating with our electrolyte. All current that flows must pass through here, so our spectrum begins with an offset of our electrolyte. I'll abbreviate it with EL. And then, first of all, we have a structure that looks like an RC element. And for high enough frequencies, this Warburg element will be small compared to the charge transfer resistance, and we get something that looks like our familiar semicircle shape. This semicircle has a radius, which is in this case the charge transfer resistance, abbreviated CT. And recall from our introductory video series, basics of EIS, that we have a characteristic frequency omega equals 1 over RC at the very top of the semicircle. And now as we progress, where we started with very high frequencies, and now move towards lower frequencies, the Warburg impedance will increase and we'll eventually end up seeing our 45-degree angled line in the spectrum. And this spectrum would theoretically, as omega approaches 0, extend all the way into infinity, but of course we measure only until a fixed frequency. Now let's think about how the spectrum might look if we vary different parameters. For example, this Warburg impedance is dependent on mainly two things, which is, first of all, the concentrations involved, where if the concentrations are higher, the impedance is lower. The diffusion current is larger for a given perturbation. And if the species here have a higher diffusion coefficient, thus are more mobile, the Warburg impedance is likewise smaller. Now, these parameters, the concentrations particularly, also influence other parameters in our equivalent circuit model. For example, the electrolyte resistance is a function of concentration. The lower the concentration, the higher the electrolyte resistance. And the charge transfer resistance will also be a function of concentration. It might also be a function, for example, of the applied potential, and the Warburg impedance is a function of concentration. Now, in terms of frequency dependence, the resistors are not frequency dependent. The double layer capacitance has an impedance ZC double layer, which can be expressed with 1 over J omega C capacitance of the double layer. And the Warburg impedance is written up here, but it is proportional to 1 over the square root of the angular frequency. And what this means is the lower the frequency, the higher both the Warburg impedance and the double layer impedance. However, the Warburg impedance rises more slowly with decreasing frequency. And what this means is that we get a certain point where essentially the double layer impedance is much larger than the impedance in this branch, and this branch becomes the dominant feature in the impedance spectrum. And so what we have are impedance spectra that look typically something like this. They have these features where they start with a real axis offset, have some part of a semicircle, and a 45-degree angled line. However, if we, for example, draw this for low concentrations, we have, for example, a higher real axis offset, and we may have a larger diameter of the semicircle, and we may end up with a 45-degree angled line that begins already here. Now, let's have a look in the lab what different concentrations do to the measured impedance spectra.
Okay, welcome back to the laboratory. Today we want to look how the concentration of the redox couple impacts the impedance spectra. Therefore, we will use a similar setup to what we already showed in the first episode, which contains the redox couple supported by sodium perchlorate, as well as a carbon rod counter electrode, a mercury sulfate reference electrode, and a platinum working electrode. We will start off with 100 millimolar of the redox couple, and we will measure at a frequency range from 50 kilohertz to 1 hertz. Okay, then let's start the measurement. We start off again with the OCP measurement. Now, for the impedance spectra, we start off at the high frequency range and see the formation of a small semicircle, which at approximately 700 hertz turns into the 45-degree angled line of the Warburg element. All in all, okay, we still have to wait until the measurement is finished. I think now it's finished, and all in all we see that the whole impedance spectra is rather small, with imaginary component less than 3 ohm and a real component less than 19 ohm at the lowest frequency of 1 hertz. For our 100 millimolar ferrocyanide concentration, and now let's move over to 10 millimolar. Et voila! Now we have the 10 millimolar concentration of the redox couple, and as you probably also can see, the solution got a little bit lighter compared to the 100 millimolar ferrocyanide. But just let's start the measurement. Similar to the previous measurement, we will also measure in a range of 50 kilohertz to 1 hertz. Now the OCP started, and I will remove the graph. The impedance spectra this time starts off at a real axis offset of approximately 60 ohms. Now we can clearly see the formation of the semicircle, which then at much lower frequencies of approximately 12 hertz turns over into the 45 angle degree line. All in all, the semicircle has a diameter of approximately 60 ohms. And yeah, let's look how the whole impedance spectra changes at even lower concentration of 1 millimolar of the redox couple. So now the preparation of our final concentration is ready for measurement, and as we already observed before, the color of the solution got even lighter since we only have a concentration of 1 millimolar of the redox couple. So let's start the measurement. Again with the OCP. So now for the 1 millimolar redox couple concentration, we see a real axis intercept at approximately 100 ohm, and now a very, very large semicircle appears, and we're currently already at approximately 2 Hertz, and the semicircle is still not closed. Yeah, and as we see, at our lowest frequency of 1 Hertz, we still haven't reached the turnover into the Warburg line, but which would approximately appear if we had measured in a lower frequency range. To sum up our experiments, we put here the impedance spectra we measured today together. On the top left corner we see the lowest concentration, followed by the 10 millimolar concentration, and on the bottom left we see the 100 millimolar concentration of the redox couple. And here in the right corner we put all the measured impedance spectra together to give you an overview how they relate together, and you can see that the 10 millimolar concentration is barely visible, and the 100 millimolar concentration is can be faintly seen by this blue dot. To sum up all the tendencies, so with lower concentration we observe a higher intercept at the real axis, the semicircle diameter increases with lower concentrations, and the frequency at which the Warburg line appears gets lower with lower concentration.